Should be just about go now. All right. Good evening, everyone, to another episode of Dan Does Data. I apologize for any delays getting started tonight. Tonight, we are going to be talking about autoencoders. You might be asking, what the heck is an autoencoder, and why are we going to spend some time on it? Well, autoencoders are a way to deal with a problem when you don't have as much data as you want, or particularly when you don't have as much labeled data as you want. It can help you just learn some useful intermediate features, and then you can sort of start with those and continue on from there and use whatever small amount of data you have. I had a nice picture prepared, of course. By nice, it wasn't that nice of a picture. It was a kind of junky picture. But let me give you the brief rundown of what's going to be going down. We're going to use this with some font data I have from another project, but you could use it on whatever data you feel like. So when you start, you've got, put in each little one of these blobs is some feature that you've got. Maybe a pixel value or something else. It doesn't, rainfall over a week, whatever, doesn't really matter. You want to do something to that data. We'll call that encode. So you've got some smaller, simpler representation. Maybe you just got these, you're computing three numbers. These are like, supposedly in your mind, you're thinking, these are the numbers that really matter. And then you've got some other operation, which you call decode. And that, in theory, takes your three numbers and gives you back whatever your original input was, or something close to it. So that's the general idea. And you can do this in a lot of different situations. You just need something to encode, something to decode, hopefully kind of a mirror image of itself, and something to measure how close is your input to your output. So, let me make another picture here. If you do this kind of thing with, say, images, you might have some image of a smiley face, and if you build some kind of autoencoder, you might end up with a simplistic representation of it. It's hard to have a much more simple representation of a smiley face than that. Imagine that this is a really epic smiley face over here with some hair and I don't know, a nose, stuff like that. You might just get the simplest possible version of what is smiley face after you auto-encode it. But it sort of maintains whatever the core important features are. That's the idea anyway. And if you use something like neural networks for your encode-decode, you can do this with tools like Keras and TensorFlow and all kinds of other things. It's kind of a natural thing to do. The idea being you do this, where you build your autoencoder, compute all this, and then you say, all right, get rid of all this stuff. Now I've got some good weights to use. Or now I've got some good intermediate features. Now I will go ahead and compute whatever the thing is that I want to compute. Maybe, let's change the color here. Maybe you want to compute, does this belong to any one of these four classes? And you just don't have that much data. So you've already got some good features, so you've saved a lot of training on just trying to get to this point. That's the idea anyway. We are not going to go into super duper depth about how these work and what they are. I don't want to spend a super long time going into how I'm reading this data. Just know I'm going to have a bunch of arrays of fonts, a bunch of arrays of text. And by arrays of text, I mean I'm basically going to have images of text. Let's go ahead and show you some of those. Let's pick a different number here. Let me just show you a couple of the images. We've got 5 different fonts. You might have, if you've tracked my For Well Thou Knowest project, you'll be familiar with this. They're all rendering the same words at each time. What other tools can be used rather than a neural network? You could really use any kind of, in theory, you can use any kind of parameterized function to encode and decode if you want to do the kind of general stochastic gradient descent optimization. So if you have parameters that you can tweak and you have a function that converts to some intermediate features and then takes those intermediate features and expands back out to whatever your feature space is, you can use kind of whatever you want. Neural networks are just sort of natural because they have this parameterization built into them, all these different weights you can compute. But like if you've done principal component analysis, it's the same kind of thing. One more key I should have mentioned. This intermediate layer, you really should have fewer variables, features than in your input. Because otherwise you might just think, haha, I'll make my encoder spit out the same thing. I will just make my output my input, and then you're done. But then you haven't really learned anything. You haven't captured the essential features, you just use the exact same number of features, and you're not getting anywhere. So if you want a good reference, just to get used to this kind of stuff, let me call up Firefox here. Things I had up before my computer froze 10 minutes ago. Oh, hey, what do you know? So Francois Cholet has an excellent tutorial up on the Keras blog for building autoencoders with Keras. So if you search Autoencoders Keras, this will be right up at the top. And it explains what those kinds of things are. It walks through an example using the MNIST digit classification dataset. I might be referring to this at various times in the talk. This goes into more detail than I'm probably going to go into, but that's okay. I found this very helpful just for understanding the syntax of what he was getting at and how everything was working. All right, so we have taken a look at the data. This is what we're going to be working with. So we got 16 rows, we got 64 columns. We've got words that are moved around in different places. We got 5 different fonts going on. So you get the picture. This is falsely colorized. Let me change the coloring real quick. CMap equals plot.cm.hot. Hottest. There we go. And so now you see the things that are white hot are where the big values are. And the black here means there's zeros. So not too terrible. I just want to split this up into like a training, testing kind of thing, because I like to do that. This might have been what froze my computer last time. We're going to find out. I really hope it does not do that this time. That would make me very sad. Let's do that. Okay, did not crash my computer. That did not crash my computer. Okay, I think we're good. I'm not really going to need the labels here. We'll see if we get to that. So I have sort of some old model stuff from the previous project. I'm going to nuke that. We're going to reuse some code. We are going to get nrows times ncols. And our activation is not going to be softmaxed. Sigmoid, we'll say. So all I'm doing is dividing the value in the pixels by 255, so I get a number between 0 and 1. And so doing sigmoid on the end means, aha, it's between 0 and 1. This may not be perfect. They may not have the right kind of distribution. I'm not going to worry about this too much. Not too much anyway. All right, so suppose your model has, so how many input things do you want? We've got 1024 features that we can work with. That's nrows times ncols. So, simplest thing, suppose that you have, let's say a small number. Yeah, let's say a small number, 32. And your input shape is nrows times ncols. And let's do activation, I don't know, ReLU. Just for giggles, just to get started. So what's this network look like? Yeah, there we go. Yeah, let's use this one, sure. Did I lose my... There's one more... Somehow I keep losing this picture. Window, recently closed docs. Empty. Dockable dialogues. Toolbox. No. Well, fine. This network, I will never erase things. That's how this is going to work. You've got the 1024 inputs, then you got 32 things we're going to compute, and then you're going to have 1024 outputs. That's all. And so we're going to be going this way, and we're going to get pictures out that look, maybe similar. Let's do a little training and see how long. I really hope this doesn't take forever to train. That would make me very sad if it did. Tell you what. And of course, our input is the same as our output whenever we're testing. Sorry, not when we're testing. Our loss is just comparing our input to our output and seeing how close are we. That is all we were doing. So that's not too terribly complicated. Sequential model cannot be built. Models and some layers first. Didn't like that. Invalid syntax. I got too many. Int object is not iterable. Oh, this needs to be a right. It's expecting a tuple. And is that even right? I'm trying to remember exactly now. Let's see how this tutorial works. Because this is using MNIST, a similar kind of structure. 784 comma. Yeah, so we should get away with this. Go. Why? I do not understand why these toolboxes are still in the way. Go away. Go away. Shoot. There we go. Let's try that. So we just say model.summary. Zoom in on that. Computing 32 things and then back up to 1024. These parameter counts, interestingly, don't line up quite exactly. Are they 1024 off? This, no. Interesting. Oh well. Oh, it's because it's the 32. Yeah, no, that makes sense. Because in the first one, I've got 1024 bias terms, but in the second layer, this 32, I've got only 32 bias terms. So the difference should be 1024 minus 32, 992, and I bet we take this minus this. 992, boom, magic, it works. That part works. All right. Let's see if this actually runs and how long this takes. I kind of don't want to run on all the data, because that is 200,000 things, and I really would rather not do that. So, I'm going to say n data, I'm going to say n equals train flat out of a 10. There we go. Let's do the first n. And I grabbed them in random order, so this should be fine. And my test set and my train set, I believe, are the same size, so I think I can just do this. I think they're the same size. So this should speed things up a little bit. At the cost of I'm not looking at as many different examples of the same text, so it might get really confused. Alright. As always, it takes a long time to compile the first time you compile it, because the compile step is a misnomer, does not actually compile at this point. Something that still irritates me to this day. It used to. I get why it doesn't, because you might never need to get to the point where you actually need to compile it. Okay. 50 epochs is going to take me about a minute here. 2 minutes. Oh gosh, 5 seconds? Ain't nobody got time for that. Validation accuracy? Oh, pfft. Accuracy is not a metric I'm really interested in. In fact, is that something I can look up here? Where is his? I think mean squared error might be the only accuracy, the only metric that really makes sense. And actually, no, that's fine. This is just tracking, is it greater than 0.5 or less than 0.5 for determining is it a black square or a white square. And that's the only thing we'll be computing on the end, I guess. Well, no, we're doing our actual sigmoid. We're computing probabilities of it being a white square or a black square. So if you're at 0.5, that means you're essentially getting nowhere. You're making no progress. Whereas we seem to be stuck at 0.6131. We've gotten a little ways of the way through. Is our validation loss improving? It actually is. Look at that. 5.9, 4.7, 4.77. All right. It is actually learning. Despite my best efforts, the model is doing something. As always amusing to see. Always amusing to see. So if you want to go through the MNIST example, you can do that. I almost thought about doing that myself. But this is such a good guide to walk through that you can do that yourself. One thing I'm doing differently, I'm putting all my things in one sequential model. Here he makes sort of each model separately and then joins them together in the graph construct in Keras. Or the model construct as it's called these days. So that's one thing that's very different. He doesn't have validation data on his autoencoder. I don't even know if that really makes sense. And we might be stealing some of this information. This is really cool. How much longer have we got? We are a little over halfway through. Our accuracy is not improved in the slightest. Is our actual accuracy improving? 6145? It is not. I really hope there's just some weird funky edge case that's burning us. Validation accuracy still narrowly improving. So because of that, I can get a sense that, yes, okay, this model is doing better. It is learning something. If the validation accuracy were not improving, I might say, this is terrible. It's awful. It's not learning proper. I'm actually impressed that every single time it's been going... Oh, there it goes. Okay. No longer going down. See if it's stuck. Not going down by as much each time. Nature of the beast. Ugh, come on. Alright, maybe I'll let it get to 40. And then I'll cut it short, and we'll see what we end up with. What did he end up getting on his problem? Does he not show? Simple spottle autoencoder, trained for 50 epochs. He's got a test loss value of about 0.11. We are at 0.4, which is quite a bit more. We're also dealing with a larger data set, or a larger feature space. And I think a slightly wackier problem. There's more components going on than just like 10 different digits. There's a lot of different letters, and they're all rendered in these very different fonts. Granted, when you're handwriting, then they're all rendered in like everyone's font, so they're all totally different. But maybe that helps you understand specific features. All right, I guess I'm just gonna let this finish. That was not my intention to just let this finish. Ignore the man behind the curtain. That's not. Don't worry about that. You don't need to see that. Okay, so I want to just predict stuff then. So h.history. I want to see h.history of validation loss. And I just want to say plot.plot. Come on. Plot.plot of that. Yeah, so validation loss improving. And after about the first 10 epochs, it seems to have trailed off a bit. That's interesting. Whereas if you plot on the same thing, just loss. There we go. Green being the regular loss. Those are very closely matched at this point. So, and this is going down. Kind of a log, natural log kind of thing. But you might say, maybe it's done. I bet if you zoomed in, you would see it on a different scale. Okay, but we want to generate some pictures of our actual... We want it to go from the inputs to the outputs. So, let me take our guinea pigs. Whoa. Are going to be test flats. We're going to grab, I don't know, the last 10. Just for giggles. Last 5. Because I like to show 5 at a time. Oh, no. I got an idea. A very sneaky idea is an idea I have. I want... Yeah, so I'm going to need this. guinea pigs are going to be, we'll use these exact same images. I don't know if those were in train IDX. Ah, so it's in test IDX. I could say test IDX. I'm trying to see if this image I want to show is in one that it saw. That index 1970. Ooh. Is there a search or find? Limpy.where test IDX equals 1970? 984. So it does, but whatever. That's fine. I'm okay with this. I am okay with this. So just as a reminder, these are the actual data points here that we're going to be looking at. I'm going to want a 2 by whatever. And for j in range 2. Another question from the audience. Done TensorFlow, but not Keras. Did Francois make the encoder and decoder separate in Keras so he can encode and decode separately? That might be. That's not really, that's something you can do. But you can just as easily extract the weights from the model itself. And right now I'm just trying to figure out what's going on and how this is working. But you're right, that might be a way that is doing it. But once you have the model, you can say model.getWeights. And in this case, you want the weights for first 2 layers, I think. That kind of thing. And then you could reconstruct a model and you could stuff the weights in there. There's I believe a model.setWeights. Yeah. So you could respecify your model in some other script or wherever you're going to use it, whatever you're going to do. But you're right, if you specify it distinctly, that's something that you would sort of get for free at the cost of having to manage those separately. I'm doing it here just because I'm probably not going to be... We'll see how much of that I get to at some point. And I always like to look at the weights and make sure I know what I have and I'm understanding something. You know what? I haven't looked at the weights yet, but that's okay. We'll get to that. We'll get to that. All right. So that actually 0, 1. So we just need to plot these two things. And it needs to be a model.predict. How does this work now? I don't need this anymore. My guinea pigs are data 1970. And I want to grab every num phrases of them, right? So length of pigs ought to be 5. Boom, look at that. Very nice. Very nice. And we're just going to go ahead and reshape that now. I am not going to reshape that. No, hang on. Hang on a second. I will... Yeah, I'll reshape. It's like, do I want to flatten this out now, or do I want to flatten it out later? Maybe I should have flattened it in the input. Who knows? Maybe that would have been a wise thing to do. So dot reshape, and it's going to be -1, however long it is, which is 5 in this case, times 10. Say n rows times n columns. There we go. Ding. Pigs.shape. Oh, and I need to divide by 255. Otherwise, I will lose my mind. I can keep this the same since I happen to know this is the equal. But I want to model.predict, and I need to put in my data of the appropriate type. So in fact, let's just move that right here. Model.predict generates output predictions for input samples. Yeah. try that. Pigs. Pigs dot shape. Pigs dot shape. Much better. Very nice, very nice. So I can come over here and I can just say pigs of I dot reshape. Now I'm making it back into a image 16 by 64. And that should be just fine. Yeah. Everything should be good. Now watch this blow up in my face. Kaboom! That does not look like it's gotten there yet, pal. It's not that hard. It's like still computing, still thinking about it, still thinking about it. It's not that hard. It's just not that hard. We have not gotten there yet. Alright. Well, first things first, let's just make sure this works, that I can display this information. Always the first question. Alright, so that works just fine. So it's this problem. What is con? Does con have a shape? 5-2. Yeah, it does have a shape. So pigs of 0, that would reshape. I know what the problem is. My reshape I did not close off. Rookie mistake, rookie mistake. You know what? I'm going to do one other thing too. Oh, jeez. Well, let's change the color. Be adventurous. So this is what it thinks of when it tries to autoencode this. Now, you go ahead and tell me if these things on the right look anything like these things on the left. Go ahead and see if you can read the words based on this. So what I can see is that it knows, aha, with this font we tend to be a little on the high side. So don't try to write anything down here. These are all definitely white pixels. This font is really bright, apparently. This one is usually not near the top nor the bottom. I can sort of see some letter-like shapes. You know what? Maybe it's just hard. Maybe that's a bad color scheme. Let's change it from hot to gray. Maybe that'll be a little easier to see what it's really getting at. Oh yeah, that's way easier. Yeah, that's way easier to understand. Yeah. Maybe gray R. It looks like I can sort of see letter-like things in here. That might just be wishful thinking. Wishful thinking. So let's reverse the white meaning of white and black here. Looking at your data the right way, that's what it's all about. Okay, I'm not crazy, right? You see letter-like shapes showing up in here? So we had a terrible model, and it's giving us terrible results. So that's understandable. So what are things you can do if you've got, for example, a terrible model such as this? Well, one thing we could do is simply increase the number of intermediate features that we're allowing to compute. If we were allowed to compute, 1024, that might be a lot of things. And that would do, maybe much better. Another alternative would be to go the deep neural network route. Comment from the audience, at least we got the background almost right. That's right, That's just the first step. Just get the background color. Nice canvas. I would say the background is mostly wrong, actually. Most of the background is white. But that's okay. So you could just add more layers. And that might mean that you want to add more layers on the back side as well. We don't need the input shape here anymore. So that might help. It might not. You might say, well, let's compute, 64 things, then 32, and then you sort of, you tend to make it symmetric, and you go backwards. So maybe that's something that you do. How long will this take to train? Let's find out. How long? You must compile your model before using it. You must, make your model correct before using it. Invalid metric loss. Oh, right. Not mean squared error, actually. That's what I want. And we'll see how long this might. Maybe change the loss type. Yeah, I'm thinking mean squared error might just be the simplest thing to do here. I kind of like the binary cross entropy concept. It's going from between 0 and 1, but it doesn't really make that big a difference, I don't think. Validation mean squared error. I mean, but inherently, that's really the only thing we have to compare that the model compare to itself. You say you've got this input image, you can overlay the image that we have right there, and you say, all right, how similar are these two images? Because ideally, you want to get the exact same thing back out. So you could switch it up to mean squared error. There's nothing inherently wrong with that. We might do that here in a second if I... Let's see, it's taking 6 seconds, trying to do 50 epochs. The validation loss here is the downside of our situation. I do like having that accuracy metric, actually. That was kind of nice. So binary cross entropy is basically the same as categorical cross entropy, but you can use it when you only have 2 classes, and then you don't have to use the one-hot encoded format. So it's 0, it's 1, it's 0, it's 1. Except you can also have a probability. So it's as though, or a number between 0 and 1, which is what we have. Well, this mean squared error is looking better. I'm trying to think. If the mean squared error is about 0.1, we've got 1,000 things. I feel like I need another Python terminal here. I'm going to do a little math. I've got about 0.1, 0.1, excuse me. That's the squared error. So if I take the square root of 0.1, for example, you say, all right, well then the mean error is actually like 0.3. So then the final the activation be rel_u to make it a mirror. Not in this case. The rel_u would give me everything from 0 up to some arbitrary value. We might say that it's a restricted rel_u, and I don't think it has to, strictly speaking, be this mirror. It just most often is. Like your encoder doesn't have to be the same as your decoder. It just almost always makes sense to have it be very similar. Let's see what's going on here. Let's take a look at how he's doing it. So in this case, in the example, he's reading the input in, he's encoding with rel_u, and he happens to be decoding with sigmoid. So your weights are not going to be symmetric in that sense. But maybe you don't care. You might be able to get away with rel_u, but then there's nothing restricting your output from being arbitrarily large. You could have a rel_u that is not arbitrarily large. Let's go back over here. So rel_u, for those of you who don't know, looks a little something. If these are your XY axes, it is 0 over here when your input's negative, and it's just y equals x when your output or your input is positive. There are versions that say, hey, at a particular point, threshold the maximum value as well. And there's also versions that say, hey, don't make the output 0 over here, make it a small number. So you still get something. And you can tweak it and do all kinds of other fancy things to it. I should not have chosen red for this color. That was perhaps a mistake. Anyway, the mean squared error in this case, if it's 0.3 on any given object, and all the objects are between 0 and 1, that's a pretty serious error. That's the difference. You know, it's a lot better than 0.5, I'll grant. But this is also not improving super duper a lot, which is just the nature of the beast as well. We're not going to be spending so super amount of time. Change the first activation of sigmoid. That is definitely something we can do. Oh, change the first one. I see what you're saying. I see. That's an interesting idea. You know what, let me kill this session. Let me interrupt this model. Let's finish that epic. Alright, I don't have time for that. We already have our pigs. We don't have our pigs. Let's see if this new model is any better. I think the answer is no. That's a negative on that one. Does not really look better. Like still, I swear like there's letter-like objects. There's the tops of letters and the bottoms of letters. It knows that those are things that should exist. And we might need to use more data. We might need just more training. You can see the model kept improving over time. The validation loss kept going down. I am going to go back to accuracy, though. I like that. That was a good accuracy. That was a good just overall metric of, is it on the right side of being on or off? Is there ink here or not? That was to me interesting. So that didn't quite do it. So another thing you can do, I'm going to have to refer to, if you're trying to, say, classify images and things, a common thing to do is convolutional neural networks, where you look at small little slices of the image at once, small little slices of the image, compute some small feature there, and then move over a pixel and do the same thing again. And now you've got sort of a new image of whatever these scores of little features are. And you do this for many different features, so you get an image of many, many dimensions at that point. You've got an image of how much of the dog nose is here. You've got an image of how much of a cat face is here, and so on and so forth. And so then you can play the game again. You can play the same kind of game here. We're going to be skipping down a couple things. I think. Convolutional. The catch is, you can do convolutions just fine. That's totally normal. You get down to some encoded portion. How do you go then from your convolved stuff back up? You need to upsample is what it is. You've got far fewer features. You need to recreate the structure of your input output is all the same thing at this point. You need to expand, and so that's what upsampling 2D does. Let's try to do that. And I am no longer training flat things. We are not data flat. Where's drunken foul blinking? I'm just gonna call it train. It's not flat at all. There we go. Just data.